Hello, this video will describe the NashDB demo proposal, a demonstration of an end-to-end system for fragmenting, replicating, and provisioning elastic databases. While on-premise data centers require enterprises to purchase enough computing resources to handle their maximum possible workload, elastic systems can expand and contract to match the application's requirements. This promises a decrease in cost, realizing savings during lulls in database traffic. However, elastic systems also introduce a number of complexities. Consider a logical relation with 100 tuples, shown below. One could fragment such a relation into 3 pieces and then replicate those fragments onto 3 cluster nodes. However, if a database workload shifts, it may be desirable to refragment and reprovision the database, as shown. These decisions, fragmentation, replication, and provisioning, are generally handled in ad hoc ways by application designers. The challenges of these issues are further complicated by query prioritization. This demonstration will showcase NashDB, an end-to-end system for automatically handling these decisions in a way that respects the user's needs. The primary intuition behind NashDB is an economic model of queries and data. We model each query as a customer willing to pay a certain amount of money in order to access data. This price represents the query's priority. Cluster nodes are modeled as firms, which offer data to queries for a fee and must themselves pay fees to store the provided data. NashDB operates under a traditional DBMS, replacing its storage layer. Instead of requesting specific blocks from disk, query operators instead request these blocks from NashDB. While receiving requests, NashDB keeps track of the monetary value of each tuple in the database. This value is based on the tuple's access frequency and the priority of the queries accessing the tuple. When the database workload shifts, NashDB begins a cluster reconfiguration. Using the track tuple value information, NashDB partitions the database into fragments, seeking to group together tuples with similar value. Once the database has been split into fragments, NashDB computes the storage cost of each fragment as well as the monetary value of that fragment to the user. Based on these two quantities, NashDB selects a replication factor for each fragment. Finally, NashDB packs each replica onto a cluster node. This process allows NashDB to adapt to changes in workloads in both complex scenarios and in real time, as we will see next. Our first scenario allows audience members to observe NashDB's behavior over time on a real-world workload provided by a large corporation. The left-hand side shows the tuple value graph for the fact table. The x-axis represents a tuple's position in the table, and the y-axis represents NashDB's estimate of that tuple's value. Each colored bar corresponds to a fragment. Using the arrow keys, audience members can progress the workload forward in increments of 10 minutes. The right-hand side shows the current cluster configuration. We highlight over-replicated nodes with blue and under-replicated nodes with red. Since the database workload has now shifted, the red fragment is under-replicated, getting significantly more traffic than it was previously. When the cluster configuration becomes out of sync with the workload, NashDB automatically reconfigures the cluster. Audience members may click and drag the scrobbler to move through the workload. There's also a play button to advance automatically. The lower half of the screen shows a static value-based partitioning method would work on the same workload. Users can compare the QPS and the cost for both approaches, showcasing the strength of elastic systems. Users can also select a second dataset. In our second scenario, audience members can interact with a live NashDB system. Queries from 7 different templates are submitted to the system every quarter second. Again, the tuple value graph and the cluster configuration are shown. The bar graph in the upper right shows the average latency of each query type. Here, audience members can adjust the volume and budget of a number of fixed queries and a customizable range query. For example, if we increase the budget of query 1, we can see NashDB reconfigure the cluster on the fly. After a few short moments, the latency of query 1 is noticeably decreased. Audience members can also switch to a live line graph display. Adjusting query volume and budget will allow audience members to gain an intuition for how NashDB adapts to dynamically changing workloads.